However, what also happens when you study such problems and you have a lot of very good people, very motivated people working on it, it can happen that some technologies are developed that have a broader application. So for instance, accelerators that were indeed initially developed for particle physics, nowadays most accelerators in the world are in hospitals and are used for tumor irradiation.
Welcome to Chelonia Podcast, a podcast about the use of scientific discoveries of technology applications. We provide the best information on projects participated by Chelonia and many more. My name is Gabriella Bernardi. I'm a science journalist, and in today's episode we talk about particle physics experiments and the research center with the Professor Beate Heinemann, director in charge of particle physics at DESY. Nice to meet you, and would you please briefly introduce yourself?
Hello, thank you for inviting me. Yes, I'm a particle physicist from Germany. So I grew up in the north of Germany and then studied physics there also, and then started to, actually during my initial studies, I was most inspired by particle physics, and so I did my PhD at a large accelerator running at that time in Hamburg. And then afterwards I went to the United States to a big experiment called CDF near Chicago. And then afterwards, actually, I started in 2007. I started to work at the Large Hadron Collider near Geneva at CERN, where I basically am still conducting my research now, in fact, and where I had several roles. I mean, so getting the experiment to work and then also managing it at a later stage. And then for all that time, I worked in the United States also a lot, and now I am back in Germany since 2016 at a research center where I, in fact, did my PhD early on. So it's called DESY, and now I just got promoted basically to director for particle physics.
Good. How did you first become interested in physics, or what or who inspired you?
I would say that I already as a kid, I mean, I liked to build things with Lego, I suppose, and I actually, and in school, I really liked to calculate things. I really enjoyed math more than anything, really. And but later, then, I mean, I think it was mostly the mathematical aspects, that the rigor that you could actually calculate what would happen if you know, some ball was thrown or whatever. All of these initial mechanics problems. I just enjoyed actually solving problems. So it wasn't really so much the big questions about the universe at that time, but rather just the joy of actually solving problems, solving equations and so on. But then I decided to study physics at some point. And during my studies of physics, only then I realized actually how much is not known. I mean, when you are in school and you learn physics, they don't really tell you how much is unknown, because all you do is solve problems that hundreds of thousands of people have solved before, like what happens if a ball you throw and how far it goes when you throw it with some velocity or whatever. But so I remember the first time I saw a problem that was intrinsically unsolvable, which is the double pendulum, where you will touch two pendula on each other. And that's a chaotic system, so you cannot actually calculate exactly where it will end up. That fascinated me, in fact. And then particle physics came then later. That I read a book by Steven Weinberg about the first 3 minutes of the universe, and I was just completely fascinated by I mean, how much one actually had already found out about these fundamental particles, and also in principle, the simplicity of them. Fascinating.
Good. Now, why it is so important, the study of particle physics?
I think it's really addressing a fundamental quest of humans, that we're trying to figure out how the world works. I mean, it's similar to people trying to figure out why there are stars, why they move the way they do. I mean, we're trying to figure out why there is the universe, how the universe actually works. And particle physics really goes to the core of that, because what we do in particle physics, it's not about counting particles. It's really about understanding what happened at the very beginning of the universe, when energies, the universe, the energies that were available in the universe for interactions were very, very high. That's why particle physics is also called high energy physics, because what we do is we accelerate particles to such a speed that the energies are as high as they were shortly after the Big Bang. And so by doing that, we can try to understand the physics laws of nature that have governed the evolution of the universe. And I think it's just a fundamental thing humankind would like to know. Now, so it doesn't have a direct application to any of the problems that we have in our world, like climate change or something. However, what also happens when you study such problems and you have a lot of very good people, very motivated people working on it, it can happen that some technologies are developed that have a broader application. So for instance, accelerators that were indeed initially developed for particle physics, nowadays most accelerators in the world are in hospitals and are used for tumor irradiation. Many accelerators are also now used for photon science, which is basically to study, for instance, viruses. Because they produce very brilliant light that can be used for that. So that's another motivation, but that's, I would say, not the intrinsic motivation, but of course it's a very welcome spin-off, basically, of particle physics.
Professor Heinemann, you have been in several prestigious leadership roles throughout your career. How have these different roles shaped your perspective of science?
Yeah, well, of science or of people? I mean, so I think both in some sense. So I think what I recognize as a leader of projects is what really is crucial is that everybody is different, right? But everybody, and that's necessary because, I mean, in these collaborations, particle physics is a very collaborative effort, and you really need very different skills and perspectives together in order to solve the technical problems that you have to address them. So what I really learned to love is actually the diversity of people, that people have diverse, of course, backgrounds, right? I mean, so they grew up in different parts of the world. They have learned different things at school, even if the school was in the same city or something. They've just learned they have different talents, and I learned to really appreciate how teams can work by putting all this expertise together, and that one can make things happen that one would not be able to do otherwise. On science, I'm not sure it has changed my perspective on science, the leadership roles. I mean, of course, my perspective on science has evolved and grown. I mean, I must say, I find it very, I get somewhat emotional when people, really huge teams come together and solve problems that are like 50 or 100 years old, as was the case with the Higgs boson, where I was fortunate enough to be a part of, but also was true with gravitational wave, which was basically a 100-year-old quest that was was solved by thousands of people working over decades in time, right? So that's amazing. But it's also with the vaccines now, that's not 100 years, it's 20 years of fundamental research, and then then a pandemic hits, and there are scientists who actually then manage to build a vaccine. I mean, so I guess these leadership roles in some sense have given me that perspective.
Now we are curious, what excites you most about your job?
I think, so in my job now, in the one that I'm taking on, I think there is a huge potential. So we really have very, very talented and very strong people. And what motivates me is I think that we get the most out of everybody to develop new ideas. I mean, I think that one of the most important things is, of course, to foster innovation, creativity. And I very much thrive to do that. And I think there's a huge potential because we have really many good, old and young, excellent people. And so, so that's what I think. I also am motivated to see to which extent also the expertise we have can help solve some of these big problems that we have in the world right now, related, for instance, to sustainability or also social justice. So that's also motivating. But it's not clear to me. So this is work in progress to figure that out.
Okay, perfect. And which skills learned as an undergraduate student serve you best during your career?
I think the fun of calculating stuff. I mean, you really need to like it. I think it's not enough that you like finding out how the universe works. You have to actually like the process of solving problems. You have to like that because I was like, I enjoyed doing calculations forever. And I think the other thing is, I think that I'm kind of not scared. I mean, I wouldn't call myself brave necessarily, but not scared. And I'm happy to try tackling a problem. I might not solve it in the end, but if you don't try, you will never succeed. So I think I maybe got that from my mother or parents or something, that I may as well try. So I think I'm not scared to try stuff, and I think that's important because then you could get lucky and then you manage to solve it, and then it's awesome.
Okay, and today, do you think that the public perspective of women in science has changed over the course of your career?
Yeah, definitely. I think definitely. I mean, so when I was growing up, I mean, I never would have ever imagined that I would become a professor. And I remember also when there were very few women at that time. And at the university I studied, there was one. And it was nearly bizarre. I mean, it was just sort of, I mean, I didn't mind it so much, but that there were so few, not actively, but it was still sort of bizarre. It was not very common to have women in particular in leading positions, at the same level as men. And I remember I remember these early interactions when I realized, oh, wow, look at that. This woman is also a physics professor and she's talking to the men just like she's one of them. So that was kind of how I felt. And I don't think that it's like that. I mean, we are more now. There are definitely more. There's also been directors, really female scientists in very prominent positions. For instance, Fabiola Gianotti is the Director General of CERN. I mean, she's been inspiring to so many of us, I think, so I do think it has improved a lot. I think there's still, more room to improve, but I think we have now at least enough that we have a strong network also of women scientists. So that's good.
And what are the upcoming scientific advances that you are excited about?
Well, so it is difficult to know what the scientific advances are. So so the technical advances one can always predict, but science advancement in some sense is unpredictable because we don't really know what nature has in stock for us. So normally, so I can wish for advances. I mean, so there are some puzzles that I would really like to understand. I would like to understand why there's more matter than antimatter in the universe. We don't understand that. I would love that we figure something out about that. Also dark matter, what is dark matter? I would love to figure that to be figured out, but nobody can predict when this will be known because this is not, so there are many experiments going on that have a potential to shed light on these questions. But since we don't know what the solution is, we don't know which experiment will succeed or if any of them. So I'm actually quite honest, I'm quite happy about any scientific advance that tells me a little more about the universe. This is what is in for the long haul here. I mean, so if any of the fundamental problems we know there is in our picture of the universe, if any of them gets a little bit more clear, I'd be already quite thrilled.
Okay, Professor, now we are at the end of the podcast, and the last question is, if you could go back or forward in time, what would you like to know or discover?
Well, okay, if I could go forward in time, I don't know to which year I have to go, but I really, more than anything, I would like to know why the electrons has a heavy brother. so there's 3 copies of electron, one of which we call electron, and there's 2 more which are just heavier versions of it, and there doesn't seem to be any good reason for that whatsoever, and the same is true on the quarks, doesn't matter. But so that is what I would like to know most. Already when I was a student, I spent hours and hours in my room trying to figure out some pattern on why, because it's not even regular, at least not that it seems chaotic somehow how the values of certain parameters are picked, and that's what I would like to know, but I don't know which year I have to go to.
Okay, fantastic. Thank you so much, Professor Heinemann, for joining us today at this podcast, and thanks our listeners. If you have any question about today's show, you can get in touch on Chelonia Twitter, and feel free to subscribe Chelonia.Smith website and be part of the community. In the meantime, stay tuned for our next interview. Bye-bye.
Bye.